Oh, sorry, apologies to those who are going to look at this on YouTube. I only now started the recording for that. That's how it goes. Anyway, this fills up with the same kind of liquid up to some height h, except now we measure the height h from the top of the liquid to the center line of the stagnation probe. So the pressure at this point out here, again, looks like a rho GH term. But we have a special name for that pressure. This is not just the regular pressure that we're used to. This is a special kind of pressure. It's called the stagnation pressure. The reason for that is if I look upstream and I pick a streamline up there, and I imagine that streamline connects to that point right at the end of the probe. Let's say this is my streamline. There is a velocity further up the streamline. Let's call that point 2. What's the velocity at 1, though? 0. How do you know? It's steady state in the tube. Well, it's steady state everywhere. What's unique to the tube that's not happening outside the tube? There's no flow, right? So even at steady state, there is no flow here, but there is flow on the outside. So we can write a Bernoulli equation going from point 2 to point 1. And if we do that, we will have the pressure at 2 plus 1/2 rho V2 squared plus rho GZ2 is equal to the pressure at 1 plus 1/2 rho V1 squared plus rho GZ2. Oh, sorry, yeah, Z1. So that's a Bernoulli equation from 2 to 1. Since I asked you guys to do it, I should probably be consistent. 2 to 1. So the pressure at 2, we're going to leave it alone. We're interested in figuring that out. The velocity at 2 is something. We don't know what it is. Z2 and Z1 are usually the same. If the pipe way up the line bends down, that's okay. Just imagine this imaginary streamline is right in front of this thing where there's no curvature. So we'll say Z2 is actually equal to Z1, so we can get rid of that. So Z2 goes away, Z1 goes away. We'll leave P1 alone. P1 exists, but V1 is 0, right? Because this is a stagnation probe. This is called a stagnation point. The velocity at a stagnation point, if the word doesn't give it away, is 0. So we can mark that off. Therefore, what we end up with is not so much P is proportional to rho GH, but now the pressure at 1 is equal to the pressure upstream at 2 plus a velocity term. So you can imagine if the velocity up here is going a lot faster, that momentum has to go somewhere. The momentum will hit this stagnation point and effectively force that height to go even higher. So what we're really measuring with the stagnation probe is not just the static pressure like we saw before, but this combination of static pressure and a velocity term. So wherever you see a stagnation probe stuck inside your system, what you're really measuring, I'm just going to erase what I had up there, is called the stagnation pressure, which we abbreviate as P0. That means stagnation pressure. You are measuring stagnation pressure, which is exactly defined. This is not an assumption or anything. We define it this way, as whatever the pressure is at that point, plus 1/2 rho V squared. If you have your probe set up this way, and this fills up with liquid, the pressure here is exactly balanced by the pressure head over here. That's how this thing makes its measurement. So this is what it's measuring. The way that it's measuring it is you're going to measure the height of that liquid column. And whatever the height of that liquid column is will produce a pressure at that point, which is exactly balanced by this term. So the way to make a measurement on that is to say, well, I know I am measuring P naught, and I know that at that point, P naught is exactly equal, now I'm going to switch to purple, rho GH, where this value is H, that height that I've sketched right there. So that's the difference between a stagnation probe and a static probe. A stagnation probe measures this entire quantity. A static probe only measures that first quantity, just the static P that shows up in your equation down here. So to demonstrate a couple of these, we have some experiments. Now, your other alternative was to watch a YouTube video for the next 30 minutes. I opted to do this because I haven't spilled enough stuff on me yet today. Some idiot who I will not name but has long hair and wears a tie spilled his juice on me at lunch. So I will also record this for anybody who wants to take a look at it online. Stop this other recording. So this is the system that is on that video. Fluid is going to come in to the right, fill up this tube to a certain extent. That tube corresponds to the one on your right, which is the stagnation probe. And what we are measuring is one pressure here. We can call that the pressure at A. Which one's measuring that, static or stagnation? Static. So the pressure at A is just equal to rho g h1. And we're going to call that distance here h1. We are also measuring the pressure at B, which is at the inlet to the stagnation probe. And that one is similarly filled up with liquid to a different height. I need to extend my tube a little bit because that height is always bigger. Which one is always bigger, stagnation or static? Every time the stagnation is bigger than the static. So that one might come up to here, get filled up with liquid. By the way, the liquid is coming in this direction. And we have another height, which I guess I'm using green for this one, which we call H2. Remember, this one goes all the way down to whatever the level is that the stagnation probe has been inserted into your flow field. So that becomes H2, and therefore the pressure at B, is it the pressure at B? Not technically, right? This is actually the stagnation pressure. So P naught at B, and technical is the best way to be correct. P naught B, or P sub 0 B, is equal to rho g h2. Right, there's just a static pressure head sitting down here, starting from the center of the tube, going all the way up to the top. Another static, or hydrostatic gradient from here to here. Remember I said if the tubes are small, we can neglect the difference between these 2 points, right? There is a little bit of a hydrostatic difference between the two. There's a column of liquid there. You can use the Bernoulli equation across the streamline to find out what that pressure difference is. It ends up being exactly hydrostatic because the streamlines are straight and you're just going normal with the streamline. So if this pipe is 1 centimeter in diameter, you have about half a centimeter worth of pressure here versus about 15 to 20 centimeters of pressure difference there. So it has very little effect on the overall measurement. So we're going to neglect that and essentially say the pressure at B is the same as the pressure at A. Which is a pretty common way to use these 2 probes. The idea is, like on an airplane, they bring these 2 points almost right on top of each other. They're very close to each other. So that becomes an excellent approximation, which is good if you're in a pressurized aluminum tube at 700 miles an hour. You would like to have a good approximation. So we therefore know P naught B is equal to the pressure at A plus 1/2 rho V squared
And I'm going to have to switch over to another slide because I don't have room to finish this up. Oh, wait, yeah, I do. I have that whole other half. Let's move that instead. So what we have then, P naught B becomes rho G H2, which is equal to the pressure at A, which we just said was rho GH1, plus 1/2 rho V squared. We can solve then for the velocity, and again, I'm going to skip some algebra here. How do we get, once we have velocity, how do we get volumetric flow rate? Multiplied by the cross-sectional area, which I already measured this, so we don't have to worry about that. What you end up getting is Q is equal to the area times the square root of 2G H2 minus H1. Does that predict a positive or a negative flow? It'll always be positive, right? Because H2 is the stagnation probe, which is always greater than a static probe. So who's got a calculator? Somebody got a calculator? Want to get out their calculator? I will tell you that A, which I measured before I got here, is 0.713 centimeters squared. And for the purposes of this problem, G is equal to 980 centimeters per second squared. And now we'll measure H2 in centimeters, and we'll measure H1 in centimeters. Not bad, right? Over like 10 minutes, this is barely gone up at all. So most of what you're seeing coming up through here is primarily diffusion. So if I measure from the top of the tube to the height up here, that is 30 centimeters. That's H1. And if I measure, remember now I have to measure from the center of the tube up to the top up here, although it wouldn't make much difference one way or the other. This is 53 centimeters. So take a couple of minutes, plug those numbers in there, see what you get. Meanwhile, I am actually going to measure the flow rate and compare it. Oh, I'll leave that up for you. We'll put our answers over here. So QP will be Q predicted, and QE will be the flow rate that I'm about to measure. I'm going to need a stopwatch for this. So to measure that flow, I'm just going to stick a bucket underneath it and time how much I collect in a certain period of time. Not the most sophisticated way, but also not the worst way. Actually, I need a volunteer. Sure, why not? So when I say go, it starts. When I say stop, it stops. Okay? 1, 2, 3, go. And 1, 2, 3, stop. What do we get? 5.25. So in 5.25 seconds, I'm not circle this one in. By the way, anybody coming to my office hours today, I'm going to be a few minutes late because I have to wheel this back across the room. So in 5.25 seconds, we have collected 540, sure, about 540 cubic centimeters. So Q experimental becomes 540 cubic centimeters in 5.25 seconds. Anybody got a calculator? Run that math for me. What? 102. I'm going to round up to 103 cubic centimeters per second. Anybody plug in those other numbers? So I hear 151 and 107. What? 0.4. Did everybody get something like that? Because I thought I heard a 107. Okay, good. It should be a little bit off. But not bad. This is usually pretty common. What are some of the things that are off between the two of these? What could account for the discrepancy? The method that I used to measure it would be one. We had two people doing it, and I had an iPhone with a stopwatch on it. Probably not the most accurate way of measuring volumetric flow rate. Anything else?
Design the percentage of air.
There could be air trapped inside there.
No, the percent of air with the.
Oh yeah, just built into the graduated cylinder. Yeah, there's. In fact, it should say somewhere in here. It's usually about 5% of whatever the measured value is. There's error there. What about on the actual stagnation probe?
You're measuring the height.
The heights could have been off, either plus or minus. This might not be perfectly level, so there might actually be an angle up here. And then this stagnation probe is actually quite large compared with the diameter of the tube. Typically they're supposed to be very, very small. So if that were the size tube that I have, that would be appropriate for a pipe that's about this big. So you typically want at least an order of magnitude difference between the two. I don't have an order of magnitude pipe that I can just carry over campus. So we're stuck with it. What that means is that unlike our assumption, which is the stagnation probe has no effect on the flow whatsoever, it actually does have an effect on the flow. But we never take that into account. We ignore it. We just say that is a way for us to measure the stagnation pressure. That's all the stagnation probe does.
Right. I was confused by what you just said. So you're saying the small tip of the stagnation probe affects the flow because the tube is not that much bigger than the probe.
Correct. Correct. So what you would see if you were able to cut that apart is right in that area around the tube, you're deflecting flow. That deflection of flow, in order to minimize it, you make the stagnation probe really small, and you make the tube really, really big. And we don't have that option here, so this deflection is actually affecting the measurement. But that's only resulting in the difference between here. It doesn't change any of the calculations you need to do. Yeah?
In the static tube, those two colors will never mix, right?
These two?
Yeah.
They will eventually mix. Yeah. Why will they mix? Diffusion. Not by velocity. Our assumption is there is no velocity. Like we said before, there's a tiny little vortex down here because it's not perfect. All that's doing is serving to chuck a little bit of the blue up, but after that, it's all diffusion all the way up. So eventually, you can actually see this one has already turned purple here on this stick. That's all diffusion. That's not something I can stop in the system. If you know how to stop diffusion, you've got a future. Okay, so let's see. We've got about 20 minutes. Let's see how you would use these. Where's the best place to know how to use these probes for you guys? On a test. Let's look at an exam problem. I'm going to turn that thing on. If the stagnation will always be higher than the static if you're measuring them at the same point. If there's a change in the duct and they're split on either side of the duct, that can change it.
And then, is there any way?
Can you guys please be quiet for a minute so we can hear his question?
Because you said at the beginning that they could be equal, but
When will they be equal if they're at the same point? How's that possible? When there's no velocity. So if they're at the same point, The only way these heights can be equal is if there's zero velocity. But if I go through a duct that reduces here, the pressure out here will be lower than the pressure upstream, and depending on which way you orient the taps, then they can be reversed. But if you're measuring them at a single point, this will always be higher than that. Everybody's red, it's not coming down. So you can see as soon as you turn it off, all the fluid just leaks right back out. So I didn't flip any magical switches or anything. It's really all still there the way we set it up. So if we wanted to see how we might apply this in the most useful example we can think of, which is an exam. A previous exam problem looked like this. We had a piece of ductwork. Ooh, that is really supposed to be symmetric, but I can tell I'm going to struggle with symmetry here. That's not bad. Piece of ductwork going up, and up here, after the contraction, we had insert over here a static probe. And upstream of the contraction, down here, we had inserted a stagnation probe. So in this system, G was pointed down, and we had our flow coming in this direction. It would fill up both of these probes, with the first one to a height that we called H1, and it filled up the second one to a height, what do you think? H2. We're so clever with our nomenclature. H2. The distance between these two probes was L, and we knew the cross-sectional area. So this is A2, and the one down here is A1. So the cross-sectional area does not change from where the probe is positioned to where I label A1, or where this probe is positioned to where I label A2. After and before the contraction, the pipe has a constant diameter. All right, and so the exam question was derive an expression. We give you numbers, by the way, but at the end of the day, you first need to derive an expression for V1, knowing the other quantities. Move that out from underneath. So that means we would know the areas and the distance L and all those heights that are on there, knowing other quantities. What do you think we're going to do? Better yet, we have 10 minutes. I'm going to give you 3 minutes. Set up a Bernoulli equation that you think we should use. You can work with the people around you, but take 3 minutes, and then we'll come back, and then we'll solve this problem. So when that gets up to 2 after the 8, we'll come back.
first question we do when we do Bernoulli's, is Bernoulli applicable in this system? Is rho constant?
Yes.
Probably. Is viscosity 0? Yes. How do you know it's 0? We assumed it. We didn't tell you what viscosity is, so it must be 0. Is the system at steady state? Yes. Probably. Can we draw a streamline somewhere?
Yes.
What streamline would you like to draw?
From the stagnation to the
So stagnation to static, that's one. We could go from the bottom to the top, that's another one. Anybody choose a different kind of streamline?
Along L,
Sorry?
along the length, from the bottom to the top.
Yeah, so that would correspond, so he said along the length, but that would correspond essentially from some point down here to A1 up to A2. Same idea. Yeah, that is generally the streamline that we want to draw. I'm going to sketch the streamline over here to make what we're doing a little bit more clear. So if I take this system, and imagine the probes are not there. Let me make that a little bit wider. So we're going to take our streamline from this point up at the top to this point down at the bottom. Notice I went right through my stagnation probe. So the way that the stagnation probe was situated over here, it was at the dead center, the axial center of this tube. I've redrawn the system over here. I've taken the probes out to make it a little bit more clear what we're measuring and how these probes work. Because remember, the probes are just there to make a measurement. They're not supposed to interrupt the flow at all. So when you're trying to set up Bernoulli, if it helps you, take the probes out and do something like this. I mean, put the probes back in when you're done, but at any rate, if we wanted to say this was point 1 and this was point 2, we can set up a Bernoulli equation, like you all suggested, from 2 to 1. That would look like the following. Pressure at 1 plus 1/2 rho V1 squared plus rho GZ1. I'm going to move down because I don't think I'm going to have room there. Is equal to the pressure at 2 plus 1/2 rho V2 squared plus rho GZ2. Now let's start canceling terms. What do we know about P1? Nada, right? It exists. It's down here. What do we know about P1? Yeah, so this is usually what happens, right? Because if you were to take 1 exactly at the stagnation point of the probe, yeah, it's 0. But remember, our assumption is these probes have no effect on the flow whatsoever, right? Very tiny probe in a giant system. So if you look just slightly upstream or just slightly downstream, you'll be back on the streamline and you won't even know that that probe is there. So what is that probe measuring in the Bernoulli equation? Pressure and velocity, right? This is the stagnation probe. At point 1, it is identically measuring this quantity. It is telling you that quantity is exactly equal to rho GH right here. So individually, we don't know what any of those terms are. But as a sum, we have a direct measurement of it that does not at all influence the flow. So we know these two, as a sum, are equal to rho G H1. How about Z1? Some people say 0. I assume you're just arbitrarily setting it to 0? Sure. We'll set Z1 equal to 0. What's the pressure at 2? Rho GH2. So again, we've got a static pressure path up here at 2. It is slightly off-center from the size of the tube. Usually that's negligible. We will tell you if you need to include it or not. Well, we will tell you if you need to include it. If we do not tell you to include it, then don't worry about it. So the pressure that we're measuring right here at the inlet to the static probe is the same as the pressure along the streamline at point 2. That is what the static probe is measuring. And that is only P2.
because it's a static probe and not a stagnation probe. How about V2? We don't know V2, right? It exists, but we don't know what it is. We're asked for V1, so how would we get V1 if we knew V2? Yes, so we can use conservation of mass, right? We're going through a duct. We know the size of either side of the duct. Conservation of mass says that V2 will be equal to V1 times the ratio of A1 over A2. How about rho G Z2? It's going to be L, right? We oriented L here. We started it at the center line of our stagnation probe, and it extends up to our static probe. So we know what Z2 is, that's L. So now we can solve. We know rho GH1, right? Remember, we know the other quantities that are shown over here. So we know rho, it'll be whatever the fluid is. Gravity, I don't know. H1 is given to us as a measurement. We canceled this out because the bottom probe we arbitrarily assigned to 0. You could have made the other one 0, but then sort of been minus out. P2, we're measuring directly with a static probe. V2 is what we're after, and this last term was given to us by the geometry of the problem. So now it's a question of rearranging this. If you want to challenge your geometry, since we're pretty much out of time right now, what you should find, sorry, your algebra, not your geometry, is that V1 is equal to A2 over A1 times the square root of 2G H1 minus H2 minus L. So in an exam situation, you would be responsible for coming up with this equation, plugging in the right terms based on the stagnation and static probe. And then we have given you all of the numbers that are in here, so you'll have to plug and chug through your calculator. Okay? I'll answer your question in a minute, but I will see everybody else on Monday.